Welcome to the massive open online course on Aspen Plus. This is the fifth week. In this week, we are continuing with the lecture series on process and property analysis. We will learn these two topics in today's lecture. One is plotting of relevant data, enthalpy versus temperature, enthalpy versus pressure, temperature versus xy, pressure versus xy. Xy means the mole fractions of any component in vapor phase and liquid phase. XY, PTXY and ternary diagrams, and reporting of relevant results in tables, charts, graphs and plots. So let us begin with the analysis tool through which we can develop this TXY, PXY diagram, etc. The analysis tools are used for generating simple property diagrams for physical property models and their data. And the following diagrams can be drawn. One is pure component property, vapor pressure versus temperature. That means only one component. Then PT envelope. PT envelope means it will be something like this, where this will be P and this will be T, and this will be liquid phase and this will be vapor phase. We'll get a line, and this is the boiling point line, because as the temperature goes higher, with low pressure it will be vapor phase, and with low pressure, low temperature and high pressure, it will be liquid phase. So this is the boiling point line, and we will have the minimum over here. This is the boiling point at 1 atmosphere, and we will have a critical point. So the graph will end somewhere at the critical point, which will be critical pressure and critical temperature. So this is called PT envelope. And then for binary systems, that is two component, we will have TXY diagram and PXY diagram. Then we'll discuss about mixtures. Ternary systems like three components, we will learn residual curves and phase diagram. And finally, we'll learn about solubility. And then we'll learn the inputs and results that could be saved in the form of analysis folder for later use. Now, this can be better learned through some examples. The first example that we have, it is about finding the density of acetone at atmospheric pressure at two temperatures. One is 25 degrees centigrade and another is 75 degrees centigrade. We can take the property method, which is inertial property method, and valid phases are liquid and vapor. We have to go to the Aspen Plus simulation window. So let us press acetone over here. And we have to select a property method. Let us choose inertial and then run. Now it's pure component analysis. So we have to bring in the pure component over here. So this is the pure analysis. So if you click, so there are various property methods like thermodynamic, transport or all. So we choose thermodynamic property method, and they have asked us to find out the density, which is given by rho. So rho is the density of a pure component. So choose rho in kg per meter cube. Valid phases are vapor and liquid. Now we have available component acetone only, so just select acetone. Pressure is 1 atmosphere. and we can give the list of temperatures. Temperature can be given in the range 0 to 100 degrees centigrade with a 50 interval or 20 interval or 10 interval as per your choice. Or you can give in logarithmic or list of values. So we have two temperatures over here, 25 degrees centigrade and 75 degrees centigrade. So we give list of values. So let us write 25 degrees centigrade and 75 degree centigrade. Now we have to run analysis. Press it. So it's running and the results are available. So you can see the green line is liquid raw acetone, that is the liquid acetone density, which is around 786 kg per meter cube at 25 degrees centigrade, and it is 725 kg per meter cube at 75 degrees centigrade. So this is liquid density. Now this vapor density curve, the blue one, is not of any relevance because you know that at atmospheric pressure and at 25 degrees centigrade, acetone is liquid. But just because you have given two phases, that is vapor and liquid, it has given some result. So in this case, we disregard the vapor raw acetone because acetone is not in vapor phase at this moment. So let us go to the next example. Here they have asked us to find specific heat in kilojoule per kilomole Kelvin of water at atmospheric pressure and within the temperature range of minus 50 degrees centigrade to 150 degrees centigrade. So we know at atmospheric pressure, water is solid in ice form from minus 50 degrees centigrade to 0 degrees centigrade, and then from 0 degrees centigrade to 100 degrees centigrade it is water, liquid water, and above 100 degrees centigrade it is vapor. So all three stages are available. Here also use NRTL property method, and as expected valid phases are solid, liquid and vapor. Go back to our Aspen window. In specification, add water, press next, run. Okay. Now let us again bring in pure analysis. Here you have to choose water, not acetone, and specific heat, constant pressure heat capacity of a pure component in kilojoule per kilomole K, and valid phases are vapor, liquid and solid all. And we have minus 50 to plus 150. This is the temperature range, and let us take number of intervals 50. So there will be 200 by 50. So every 4 degrees centigrade we will get one data point. Pressure is 1 atmosphere, keep it like this and run analysis. So you can see here, as we have discussed just few minutes back, up to this point, this is ice, solid water, and above 100 degrees centigrade, this one is vapor phase, and this is liquid phase of water, this entire thing. So the green line is liquid CP. So this portion is relevant for this curve. This portion is not relevant, this portion is not relevant. Because at 1 atmosphere, the water is not in solid phase. So this portion is not relevant at all. So as this. What about the red line? It is solid. So this portion is relevant, not this portion. And finally, vapor CP water, it is blue line. So this portion is relevant, not this one. So that's how you analyze the specific heat of water at various phases. And the next example is of finding Gibbs free energy of pure ethanol at equilibrium condition within the temperature range of 0 to 500 degrees centigrade and at two different pressures, 1 bar and 20 bar. So go back to your specifications, add ethanol over here. They have not asked us to use any property method. Let us keep inertial only. Run. Okay. Now let us again choose pure. Here it is gives free energy. So this is one, gives free energy of a pure component, ethanol. Unit is kilojoule per kilomole, let us say. And at two different pressures, 1 bar and 20 bar, keep the temperature range from 0 to 500. So keep it 0 and here 500. First, let us say at 1 bar, run analysis. So this is the G versus temperature. And if the same thing, if you do at 20 bar, you will get this curve. Okay. Now you can always plot these two graphs in the same one. So for that you have to add in the pure once again. So bring in pure once again and bring in G. Ethanol 500 and this is 1 bar. So for pure 3 we have already taken for 20 bar and we run the analysis once again. So this is the plot. Let us change the legend. It is for 1 bar. And this one is for 20 bar. Okay. Now we merge these two plots. Merge it with G plot. So you can see two plots are merged. Let us move the legend over here. Here you can see the blue line is this one, that is for 1 bar, and this is for 20 bar. The green line is for 20 bar. But don't think that they are almost superimposing each other, because the y-axes are at different scale. Although their temperature scale is same, 0 to 500. Now we can compare it better way by merging the y-axis. So for that we have to press y-axis map and press single axis and press OK. Now it is better. So we have single axis, and you can see at any particular temperature, say 250 degrees centigrade, the Gibbs free energy of ethanol at 20 bar is minus 105,000 calories per mole. So you can change the unit also. Instead of calories per mole, you can use joules per kilomole or something like that. Anyway, so this curve is higher than this one. So this is the type of analysis that you can do. And you can compare your theoretical knowledge of Gibbs free energy with the result that you get. The next one, we will learn what is PT envelope. Now, as I said, PT envelope is a pressure versus temperature diagram. So it is applicable only for vapor liquid system, not for liquid liquid system. And it forms an envelope for mixture compound. For pure component, it is something like this, because it tries to find out the critical pressure and critical temperature point. But for mixture, it creates a kind of envelope where you will have a dew point line and a bubble point line. So that actually differentiates the area of liquid vapor and vapor liquid mixture. And it can mark for 0 to 100% vapor. So to understand it better, let us take this example first. So it says, obtain a PT envelope for pure benzene, pure toluene, and pure water at 1 bar. Use inertial property method, merge the plots. So let us try this. For that, let us go back to Aspen simulation window and look for benzene, toluene, and water. Water is already there in our specification. So let us add benzene and toluene. Okay. So press next, run. Yes. Now you can call PT envelope. So here for benzene, just give 1 kilomole per hour. Don't give anything else, because you are looking for pure benzene. So you have a flow of benzene, only benzene, nothing else. And pressure, it should be 1 bar. So let us say 1 bar pressure. And then run analysis. Yes, so you can understand that at 1 atmosphere pressure, boiling point of benzene at 1 atmosphere is 79 or 79.5 degrees centigrade, whereas the critical temperature of benzene is 287 degrees centigrade and critical pressure is 47.8. So let us write it for benzene. Okay. Now let us bring the second PT envelope. It is for toluene. So just give 1 kilomole per hour. It doesn't matter, you can give 10 kilomole per hour also, or any number you want. Just you have to mention that it is a pure liquid. That means only one of them is going in, not others. Here also you press 1 bar and run analysis. So here also you can find that at 1 atmosphere, the boiling point of toluene is around 110 degrees centigrade, whereas the critical temperature and pressure of toluene is 318 degrees centigrade and 40.7 bar. Just change it to toluene and bring in the PT envelope once again, and this time you have to choose water at 1 bar. Run analysis. Yes. Now water is very common liquid, and you know what is the boiling point of water at 1 atmosphere. It is 99.6. It says 99.6 because it is not 100. Why? Because we have measured it at 1 bar, not 1.01625. Because actually 1 atmosphere pressure is 1.01625, but we have measured it at 1 bar. So the boiling point of water here, it is showing 99.6. Anyway, we can see what is the critical pressure and critical temperature, and you can see it is 373 degrees centigrade and 217 bar. That is the critical pressure. So let us change it to water. Okay, so we have got PT envelope for pure benzene, pure toluene and pure water at 1 bar using inertial method. Now they are asking us to merge the plot so as to compare the PT envelopes of 3 liquids that we have got. So for that, let us merge plot. So merge plot with PT envelope 2 and then with PT envelope 1. Okay. Now everywhere they have taken a separate y-axis for themselves. Now we want to merge them all. So go to y-axis map, make it single axis and press OK. So this is water, and one of them will be benzene. I believe this is benzene. Okay, so this is benzene curve, this is toluene curve. So benzene is blue, Okay, so you can compare the PT envelope curve of these three components, benzene, toluene, and water. The critical temperature and critical pressure of benzene is this one. This is for toluene and this is for water. And the boiling point at 1 atmosphere are also given. This is for water, this is for benzene, and this is for toluene. So that's how you get the PT envelope for three pure components. Now the next one, we will learn binary analysis. Now the name suggests it is for only two substances or two components. And we can find out the TXY diagram and PXY diagram. Also we can see the Gibbs energy of mixing. The valid phases we will have in binary analysis: vapor liquid or vapor liquid liquid. Also vapor liquid with either free water or dirty water. So many valid phases are possible for binary analysis. Now in the second example is asking for PT envelopes for ethane pentane mixture at 1:1 ratio and 1:3 ratio using Peng-Robinson property method. So we have to bring in ethane and pentane over here and take a mixture of 1:1. So let us go back to specification. None of ethane and pentane are there, so we have to add in both of them. So ethane and pentane. Okay. Now we have to choose Peng-Robinson property method. Peng-Robinson property method. Press next. Okay. Now again you bring in PT envelope, and here you have to give 1:1 ratio ethane and pentane, and it's not, the pressure is not given, but we can take 1 atmosphere. Let us take 1 atmosphere. Yes, so you can run analysis. Here you can see there are two items. One is pentane and another is ethane. Now this line, this green line, is vapor fraction 0. That means it is completely liquid line. And this blue line is vapor fraction 1. So it is a completely vapor line. So this is actually the dew point line, and this is the bubble point line. Okay, so in terms of vapor liquid mixture, we can argue that this entire area over here, this entire area, this is liquid, and this entire area this side, it is vapor, and in between we have vapor liquid mixture. So this is a perfect envelope we have, where we have one bubble point line and one dew point line like this and this. Now first we'll learn TXY diagram. Now this TXY diagram, here the temperature varies but the pressure is fixed. So this will represent the X, that is the mole fraction of component in liquid phase, and this is mole fraction of component in vapor phase. So this will be the dew point line and this is the bubble point line. So this TXY diagram will have. And the inside portion of the envelope will represent the vapor liquid mixture. So this is the portion, it will be vapor liquid mixture. And the upper line, dew line and bubble line we have already discussed. Now let us go to this example. Obtain a TXY diagram for the following two systems at 1 atmosphere pressure. One is ethane pentane system. It's an ideal solution because ethane pentane system, if you see the vapor liquid equilibrium, the VLE diagram, the experimental result and the ideal model simulation result will almost merge. So it's an ideal solution. Ethane and pentane, they do not have much molecular interaction. Whereas water phenol system, it's a real solution. Here they have said that use both ideal property method as well as unifact property method for the above cases and compare. And obviously the valid phases are vapor, liquid, liquid. Now water phenol system will have vapor, liquid, liquid because water and phenol, they do not mix much. So let us go back to simulation window. Here we have to take ideal process. So ideal property method and binary diagram with ethane and pentane. So choose ethane, pentane. Okay. And starting point of mole fraction of ethane is 0, end point is 1, number of intervals 50, and obviously it is 1 atmosphere. At 1 atmosphere, so 1 bar. And you can run the analysis. So this is the ideal case. Okay, this is the ideal case. Now the same thing we can try with unifact model. For that we have to bring in unifact property method and run it. Okay. Then go to the binary method and ethane, pentane, the calculation option, it will be unifact, valid phases, vapor, liquid, liquid, run analysis. So this is the second one, ethane and pentane. Now let us change this thing with unifact so that we can differentiate with ideal case when we merge the graphs. Now merge the graphs. So merging plot with binary, this one, Merge the axis also. Yes. So you can understand for ethane pentane binary mixture, whether you take ideal model or unifac model, their TXY diagrams almost match with each other. Now let us take water phenol system instead. So this is water. Okay, we do not have phenol over here, so let us go to components and add phenol. And then next, run. Okay, go to binary. Take phenol over here and water over here. Mole fraction from 0 to 1 of water. Calculation option unifac. Okay. So run analysis. Okay. This is unifac. Now same thing if you want to do with ideal system, then check what happens. Okay. So this is the ideal case. Okay, it has overwritten, so we do not have the previous one. Let us bring in. Let us bring in the second one. So choose phenol, choose water, and calculation option unifac. Run analysis. Okay, let us open, rename it unifac. And then merge the plot with binary plot 3. So this pair is uniform, unifac, red and magenta color ones. Edit Y-axis, merge them. Here you can see, although the dew point lines of both unifac and ideal cases are somewhat similar, but the bubble point lines are far apart. So it is understandable because water phenol system is not an ideal system. it is a real solution. So we have to use activity coefficient model, not an ideal model. So that's how we generate TXY diagram. Similarly, PXY diagram can also be found out. Here the pressure varies, but temperature is fixed, typically at atmospheric condition, that is 25 degrees centigrade. Here also the XY composition of species I will be shown, and because it is a PXY diagram, so upper line will present X as well as bubble line, and lower line will present Y in vapor phase as well as in dew line. And the inside portion of the envelope will present the vapor liquid mixture. And actually this figure will be something like, this will be your PXY diagram. Unlike TXY diagram, which was something like this, it will be something like this. So let us solve this problem. Obtain PXY diagram for the following two systems at 25 degrees centigrade. So our systems are same, the methods are same. We'll do only one of them, and the rest you can practice yourself. So for that, instead of TXY diagram, we'll have PXY diagram for water phenol. Calculation option, UNIFAC, run analysis. Yes. So you can understand what it is. It is at 25 degrees centigrade. This is the bubble line, and this is the dew line. This is X, actually it is XY. This curve, this axis is XY axis, liquid vapor mole fraction of water. Okay, and visibly this is liquid portion, this is vapor portion, and inside it is liquid plus vapor mixture. Okay, so this is how you can get a PXY diagram. So you can practice the other ones. I have done PXY diagram at 25 degrees centigrade for water phenol system using UNIFAC. So you can try out with ideal property method, and also you can change the components to ethane and pentane and try out both ideal property as well as UNIFAC property. Others will remain same. Now let us learn Gibbs free energy diagram. Now as you understand that Gibbs free energy for a process or reaction, if the Gibbs free energy is decreased, then only the spontaneity of that reaction or mixing that will be established. Suppose the Gibbs free energy of a pure component I is Gi naught, and the Gibbs free energy of the same component I in a mixture is Gi, then Gi has to be less than Gi naught in case of a spontaneous process or a reaction. So suppose it's a binary mixture, then this is the Gibbs free energy of component 1, and so this is the Gibbs free energy of component 2. If it is a 50-50 mixture, then Gibbs free energy should look like this. Then only the system is spontaneous or the mixing is spontaneous. If the Gibbs free energy diagram is something like this, then it is not a spontaneous reaction. Or we can conclude that these two components are not miscible at all. Okay. Now we shall learned this Gibbs free energy diagram through this example, where they have asked us to obtain a Gibbs free energy diagram for ethane pentane and water pentane systems. As we know, ethane pentane is a nonpolar type of system, so it is an ideal system. It can mix, whereas water pentane system is polar nonpolar, so it is not miscible at all. You can use unifact property method for running this. So let us again go back to our simulation. So here, bring in binary, bring in Gibbs energy of mixing, ethane, pentane, calculation option unifact, okay, at 1 bar pressure, temperature is 25 degrees centigrade. So run the analysis. Here you can see at 25 degrees centigrade and 1 atmosphere pressure, the Gibbs free energy of mixing, it is something like this. So Gibbs free energy of the mixture is lower than the pure components. So we can conclude that this particular pentane and ethane mixture is a spontaneous mixing components. Okay, they will mix spontaneously. Now let us bring in another one, which is water pentane. So water and pentane, other conditions remain same. Let us run the analysis. Yes. So here you can see the Gibbs free energy is increasing for water pentane system. Okay. That means this mixing is not spontaneous at all. Okay. This system is not spontaneous. Now we will learn the mixer analysis. Now the mixture analysis is used for property evaluations of multi-phase mixtures from flash calculation or single-phase mixtures without flash calculations. The relevant tables and plots are generated and one or more properties can be used. Okay. Now let us take this example. Analyze the water and ethanol mixture of 1:2 ratio between 0 to 100 degrees centigrade temperature and 3 pressure points, that is 1 bar, 10 bar and 50 bar. So let us take this mixer analysis. Now before that you need to prepare a property set. In the previous lecture we learned how to set a property set. Okay, so let us enter the ID PS1 and let us say we want CPMX so this is the heat capacity CP of a mixture, and we can ask for mu mx So that is the viscosity of a mixture. And gives free energy of a mixture. So the unit we can choose as centipoise, this one as kilojoule per kilomole K, and GMX we can choose, say, kilojoule per kilomole. And the qualifier, let us say the vapor. Okay. And also you can say liquid also, no problem. If we have a liquid phase, that's not a problem. So we have set the property. Now let us take mixer analysis. Choose mixer. What are the components? Components are water and ethanol. So bring in water and ethanol in 1:2 ratio. So let us say this is 1 and this is 2. So this is 1:2 ratio. And the temperature range from 0 to 100 degrees centigrade with 20 number of intervals, and pressure 1 bar, 10 bar and 50 bar. So enter the values: 1 bar, 10 bars and 50 bars. So for 3 values we get. And what are the properties to report? We have already said there. Just select them and run analysis. So this is the mixer diagram we get. Let us say one by one. This line, okay, all the lines are almost superimposed, so it's very difficult to distinguish between them. But we can definitely look for this one. This one should be I think, liquid GMX at 50 bar. So this curve is liquid GMX for 50 bar, and its y-axis values are given. How with temperature increase it changes its value. So these are graphical representation of all the properties from this temperature point to that temperature point at various pressures. So that is how you can get the mixer properties. So we end our lecture at this point. We'll continue in the next lecture. Thank you.